Hi everyone. Today in lecture 14, we're gonna have our second discussion on sharing stress. Before begin, as we always have done, we're gonna repeat what we covered in lecture 13 in previous lecture. So to give the review on previous contents, let me give you a visual diagram and front and cross-sectional view. Okay, cross-section view. So what you're gonna do is, this is a beam, possibly under like a moment and shear force, like somewhere away from this infinitesimal, very thin imaginary volume, and this is the front view. And suppose that we are considering this symmetric cross section, and what we have derived before was we derived the equation for the force and the shear stress on this cross-sectional plane. Okay, so how we have done, so we take very thin element with delta x, such that we can just say that delta h is constant within this very thin element, and we considered a moment applied to here and moment applied to here. It's m and m plus delta m, because they are not at exactly same location, so the moment could be possibly different, and of course there could be this shearing force, but shearing force does not generate like a normal stress here directly, so we'll consider the effect of moment to left hand side and effect of moment to the right hand side surface. Okay, and if we think about the free body diagram, in addition to this stress distribution in the left and stress distribution in the right, we can also have this uh, force at the bottom of this red volume. Okay, and at the bottom of this red volume, we define this as delta H. Okay, and after setting up this free body diagram, and also realizing that within this free body, the force sum along the x direction must be 0. We can write down this equation. Okay, so this is force acting on left hand side, this is force acting on right hand side, this is force acting at the bottom. Okay, so this is the how we indicate this delta H. And please ignore all side wall and top walls, because we are not considering any force around this red volume except this delta H place. Okay, and regarding the existence of delta H, we considered this example, like we considered like a stack of this thin films, and once we try to push this down without any adhesive, it'll have this sort of sliding, but with the adhesive there is no sliding, so that we can realize that there must be force in x direction. Okay, and how can you obtain this force on left and force on right? We can just utilize the flexure formula, and you gotta be careful about the sign here, and except the sign, there is nothing to confuse. And if you plug in expression for sigma L and sigma R, this is the equation we're gonna get regarding the sum of the forces in left and right hand side, and delta H is force on the bottom. And if we define Q as delta H divided by this thickness delta X, which is the force per unit length, then we can write down by moving this to right hand side and define this as delta H over delta H x Q, and you divide this as delta X, then recognizing that this is V from our previous chapter, and recognizing this is the area moment of inertia for the cross section, and recognizing this as integral that we're gonna perform for this area, then we can write down and derive Q equals V over I multiplied by Q equation. Because Q is force divided by this delta H. If you divide, instead of delta X only, if you divided this also with thickness t, then you can define this as tau xy, tau yx. Okay, and recognize then tau yx and tau xy are equal to each other. Yeah, once you obtain tau yx, you can obtain shear stress acting on the sidewall. Okay, so this is how our logical flow was made in previous class. Okay, so here the complexity we are having is depending on the location that where we wanted to know the tau xy, we have to compute this integral again and again. Okay, and one of the example and simple geometry we considered was rectangular cross section with thickness b and height h, and when we consider location y, distance from the centroid, we can obtain qy in analytical form as a function of y, and after plug in expression for I and t, which is the constant over the entire cross section, we can write down and we can derive analytical expression for tau xy average. But this is a very exceptional case with super a simple cross section. Typically when we solve the problems in shearing stress chapter, we gotta take some efforts to obtain the q integral. Okay. And let me also give you a supplementary discussion and supplementary note. Okay, so if you think about the derivation procedure, you might wonder, like, instead of qy, which is the top of this surface, you might wonder, like, we maybe draw the free body diagram at the bottom of this volume and try to obtain the stress here, and from stress and force here, and from there we can obtain the tau xy. Okay, and of course your guess is true. So instead of using the area above the y, you can use the area below the y. Okay, so please see the difference between the above and bottom equation, and let's call this as q prime. However, when you want to use q prime, instead of q, you have to positive sign, you have to use negative sign here. Okay, so let me give you explanation soon. Okay, so previously what we have done was we considered volume at the top. This is the free body diagram that we considered in previous lecture and previous page. Instead of this, what you can do is we can take this bottom and try to draw free body diagram. Okay, so whether you consider free body diagram 1 and whether you consider free body diagram 2, they're gonna have to result in same result. Okay, but here what we have to be careful is when you define delta h here, when you define delta h prime here, because like this red volume and green volume, they give they are like action and reaction pairs, and according to the Newton's famous third law, we can very easily recognize that delta h must be minus delta h prime. Okay, so they have same magnitude but opposite sign. Okay, so here when you consider the force equilibrium in x direction, you have left and right hand side force from this flexure formula. You have the force from bottom, and they must be summed up to be 0. And for the second free body diagram, so I draw these kind of free body diagram. So you have compression above the centroid, you have tension below the centroid, and I'm taking this as free body diagram. Okay, and this must be the expression for force equilibrium in x direction. Okay, so instead of delta h, you have to use delta h prime, and because of the action reaction principle, delta h and delta h prime must have this relationship. Now let's keep moving on a little bit. So from here we can rewrite delta h as yeah, this integral, this is the famous Q integral, and from the action reaction principle you can say delta H equals to be negative delta H prime, and negative delta H prime after you move this to right hand side, the same as negative delta M over I, and the integral for this green one, which is Q prime. Okay, so now what you can realize is after removing all these, qy, which is the integral above the y location, is same as negative integral below the y location, and let's define this as a q prime. And except this, previously you have a positive sign here. Here, after replacing q with q prime, you have a negative sign here. But other than that, whether you obtain the answer from q integral or q prime integral, you're gonna get the same result for tau xy. Okay, so depending on the geometry and depending on the requirement, you can choose either q integral or either q prime integral. Okay, so it's definitely choice by convenience and no other physical meanings. Okay, so with this, let me finish and wrap up my simple and short review on previous lecture.